All right, now we're going to look at an application that you have with derivatives that concerns rates of change. All right, first of all, talking about the position function, so just the position of an object. So the function s that gives the position of an object as a function of time t. So that just means when they say a function of s, if you'll notice here, that's what they use when they're using their function notation. So the lowercase s is always going to represent what's called the position function, and it's just going to be with respect to t. They're using t for their variable just because it stands for time. Okay, now what each of the variables stand for in the position function, you've got 1/2 times g times t squared. So the t squared and the t are the variables. So we just need to talk about what g, the v sub 0, and the s sub 0 stand for. So s sub 0 is going to talk about the initial height of the object. V sub 0 is the initial velocity of your object. Now g would be one of these two values, depending on whether you're talking about feet per second or meters per second. So some of the problems that you're going to work, though, will already have this calculated for you, but if they give you the position function with that g there, you'll have to substitute in one of these two values. Of course, you'll know from the values in the problem whether it's feet per second or meters per second that you need to use. All right, next is you're going to be asked about average velocity, and when you're talking about average velocity, of course, if you think back, what we're talking about is rate of change, so that's always related to slope. So if you think about when you're finding slope, you do the change in y divided by the change in x. So average velocity is your change in distance divided by your change in time. So remember, s is your position function. So the change of that position function, so that would give you the change of the distance divided by the change in the time. So delta s divided by delta t would be the notation for that. But in a minute, we'll have a problem that'll say what's the average velocity, and you'll have to subtract the distances and subtract the times to get the average velocity. Now, instead of talking about just average velocity, you also have what's called instantaneous velocity, or, as I've said, just velocity. So if you see just the word velocity, you don't have average in front of it or instantaneous in front of it, it's understood to be the instantaneous. If they specifically want average velocity, it'll have to say average. All right, the velocity function is going to be denoted with v of t. So s of t is the position function, v of t is going to be the velocity function. So this is the derivative of your position function. So once you get s of t, you take the derivative of it, then you will have your velocity function. Velocity can be negative, positive, or zero. Of course, if your object is falling, like if you're at the top of a building, you drop a ball, then the velocity is going to be negative. The negative just indicates the direction that it's falling. Whereas if you're talking about a velocity that's positive, then that would be an object that's being shot into the air. The speed of an object is the absolute value of its velocity. Okay, so like for instance, the reason why you have absolute value is what I was saying. If you're talking about an object falling from the top of a building, the velocity would be indicated as a negative number. But then if you said, okay, well, what's the speed of it? Then you take what you just found, but just do the absolute value of it. Speed is always expressed as being positive. Okay, so here's the first problem that we're going to look at. Now, this is what I mean. Sometimes when you're given the position function, they will have already calculated the g part of it, so you don't have the g. So that means you don't have to worry about, do I need to plug in that negative 32 or do I need to plug in the negative 9.8? You don't have to worry about that on this one. Okay, so a ball is thrown straight down from the top of a 280-foot building with an initial velocity of 12 feet per second. So we got to get the position function and the velocity function. Now, this is the general format or the formula for your position function. So we just need to substitute the information from here into this. So S of t would be negative 16 t squared. Now, your initial velocity is negative 12 feet per second. Remember, v sub 0 is your initial velocity, so you've got to substitute negative 12 here. So you'd want to just write that as minus 12t, and then plus s sub 0. S sub 0 is your initial height, so that would be the 280 because the ball starts at the top of that building. So that would be the initial height. So this is your position function. Okay, next you're just asked to find the velocity. Now remember, the velocity function is the derivative of the position function. So using your power rule here, that would give you negative 32t. Taking the derivative of the next term would be minus 12. And of course the derivative of this last term would just be 0, so you wouldn't have to write that down. So this is your position function, this is your velocity function. Okay, next, you're asked to determine the average velocity on the interval from 1 to 2. So that just means from 1 second to 2 seconds, what would be the average velocity of this ball that's being dropped from the top of the building. All right, so you remember what we did with average velocity. I said that it was the change in the distance divided by the change in time. Now, to get your change in distance, that would be actually using your position function, because your position function tells you where you're located, okay? So you would need to know those two numbers to get, the distance, like what is the distance from 1 second to 2 seconds. All right, so you would need to actually substitute the 2 into the position function, subtract from that what you get when you substitute 1 into the position function. So this is how you would find your change in your distance. You would want the position at 2 seconds, and you'd want the position at 1 second, and then subtract. And then you're going to divide that by 2 minus 1. So if I do s of 2 minus s of 1, then I've got to do 2 minus 1. Just make sure you're subtracting in the same order. Okay, so when I say s of 2, that means you've got to substitute 2 into this function right here. Okay, and then you've got to subtract from that, and now you've got to substitute 1 into the position function. Okay, and then you're going to divide that by 2 minus 1. All right, so if you calculate s of 2, this first part that I have in the bracket, then you're going to get 192. And then calculate over here where we substituted in the 1, and you would get 252. Of course, on the bottom, 2 minus 1 is just 1. So that gives you negative 60, and that would be feet per second. So this would be considered your average velocity. Okay, next, you're going to be asked to find the instantaneous velocity at t equal 1 and t equal 2. So what we just finished doing was average velocity over a span of time, because we wanted to know what was the average from 1 second to 2 seconds. Now I want to know, well, what was the velocity exactly at just 1 second, and then what was the velocity exactly at 2 seconds. So since we're wanting the velocity at these two specific times, now you're going to go back and you're going to use your velocity function, which was the derivative, remember, of the position function. So you just calculate v of 1. Now it doesn't matter which one of these you calculate first. So that's going to give us negative 32 times 1 minus 12, and that's going to give you negative 44 feet per second. So that would be your velocity exactly at 1 second for this ball being dropped from the building. Then calculate v of 2. So that's going to give us negative 76 feet per second. Now, I want you to compare that to this average velocity, though. If you notice, the average was negative 60 feet per second, and that was between 1 and 2 seconds. This was 1 second, this was 2 seconds. Actually, 60 is exactly halfway between these two, because this is your average. And this was like the bottom, and this was like the top, like from 1 second, and then the other at 2 seconds. Okay, next. You're asked to find the time required for the coin to reach the ground. All right, so this is going to require the position function, because if you're talking about when it reaches the ground, that means your position is going to be at 0. Like when you say position, that would mean like the height of this ball. So when it hits the ground, there is no height. So you're going to take your position function, and like I said, you're setting this equal to 0, because that 0 is the height. Now, you can try to factor this. I don't know if it factors or not. I'm just going to use quadratic formula. So I would have this. Okay, so simplifying this just a little bit. All right, you do the calculations under your radical, you're going to get 18,064. Okay. If you put this in your calculator, like first of all, of course, put it with the plus sign. If you put it with the plus sign, you're going to get negative 4.6. Then if you do the calculation using the minus sign, you're going to get 3.8. This is going to be your answer because you're solving for t, which is a time. You're not going to have a negative time. So this means find the time required for the coin to reach the ground. So it's going to take 3.8 seconds for this ball to hit the ground. That's what you have figured out. All right, one more question with this problem is it asks that you find the velocity of the ball at impact. So what is the velocity when it hits the ground? So we're actually going to use what we have found in D part, because remember, D part is where we found the time that it took to hit the ground. It took it 3.8 seconds to hit the ground. But now we want the velocity. So velocity, of course, means that you need to use your velocity function. But t is time. Well, we just found out it took 3.8 seconds for it to hit the ground, which would be the same thing as saying impact. So all you do here is substitute the 3.8 into the velocity function. So what is the velocity specifically at this time? That's, again, what you're asked to calculate. That's negative 133.6 feet per second. Now, if you remember, we saw like at 1 second it was like 44, at 2 seconds it was 76, so now at 3.8 it's made it up to 133.6. But that should make sense because the longer it falls, the faster it's going to be. It's going to pick up more speed as it falls.